A system of equations may have a unique solution, infinite solutions, or no solution. This lesson is about infinite solutions. When a set of equations has more unknowns than the number of useful equations, there is not enough information to solve these equations. We can try to provide more information in the form of one or more parameters. By varying the values of these parameters, we get different solution sets that satisfy the equations. Since we can pick any real number as parameters, we can generate infinite numbers of solution sets. A system with infinite solutions is considered consistent because we are able to get solutions to the system. Sometimes, just by looking at the system of equations, we can identify whether the system may have infinite solutions, such as if we notice that the system has more unknown variables than the number of equations. Also, some of the given equations may be multiples of each other, which means that we actually have fewer useful equations than the number of given equations. After row reducing the system of equations in an augmented matrix, look for columns that lack leading ones. Each column without a leading one may mean that we need to provide extra information in the form of a parameter to solve the system. Here are some concrete examples. Let's say we have a system of equations with the variables v, w, x, y, and z. We have a leading one for v and a leading one for y, but notice that we do not have a leading one for w, x, or z. We need parameters for these three variables for which we do not have a leading one. In another system, let's say we have the variables a, b, c, and d. We have a leading one for b and for c, but we do not have a leading one for a or d. So we need a total of two parameters to solve the system. One parameter for a and a different parameter for d. In this system, we have a leading one for all three variables, star, flower, and diamond. So to solve the system, we actually don't need any parameters. Did I trick you? Solve the system of equations. There are three unknowns, x, y, and z, some people call it z, but only two equations. This will be a case of infinite solutions. We begin by organizing these equations into an augmented matrix. There will be two rows corresponding to the two equations, and three columns of coefficients corresponding to the coefficients for x, y, and z. First column is x, second column y, and third column z. The last column is going to be what I call the answers. Some people call them constants. The first equation, we have 0x, negative 2y, 12z, and it's equal to negative 3. The second equation has 2x, 6y, and is equal to 1. Having set up the augmented matrix, our task now is to use row operations to get the matrix into reduced row echelon form, which means non-zero rows have a leading 1, and each column with a leading 1 has zeros everywhere else in that column. There are many ways to row reduce this matrix. What I'm showing is just one of the ways. My personal strategy is to look for common multiples between rows, and then add or subtract rows to cancel those common multiples. Also, I like to use rows with more zeros to get zeros in other rows. Looking at the negative 2 and the 6, there's a common multiple of 6. If we multiply that negative 2 with a 3, we get negative 6, and then add to that 6 to get a 0. Let's do that. Row 2 plus 3 row 1. 2 plus 3 times 0 is 2. 6 plus 3 times negative 2, so yes, we do in fact get the 0 that we want. And then 0 plus 3 times 12 is 36. 1 plus 3 times negative 3 is negative 8. Notice that there is a common factor of 2 in this row. We can divide all the entries by 2. Let's go half times row 2. Half of 2 is 1, half of 0 is 0, half of 36 is 18, and half of negative 8 is negative 4. We're now almost done row reducing. The leading non-zero in each row has zeros everywhere else in those columns. Let's start getting leading ones. In the first row, if we divide all the entries by negative 2, we get a leading 1. Let's go 1 over negative 2 multiplied by row 1. 0 over negative 2 is 0. Negative 2 over negative 2 is that leading 1 that we want. 12 over negative 2 is negative 6. and negative 3 over negative 2 is 3 over 2. In reduced row echelon form, we want to get the leading ones in the staircase pattern from the top left corner to the bottom right. We can interchange rows 1 and 2. This matrix is now in reduced row echelon form. We have a leading 1 in the x column and a leading 1 in the y column, but no leading 1 in the z column. Therefore, we're going to let z be a parameter. Let's call it t. We now interpret this matrix to get the solution set for x, y, and z. In the first row, we have 1x plus 18z equals negative 4. Solving for x, we can subtract 18z from both sides. Since z is equal to t, we replace that z with t. X is equal to negative 4 minus 18t. The second row tells us y minus 6z equals 3 over 2. Solving for y, we add 6z to both sides of the equation, and then replace that z with t. Y is equal to 3 over 2 plus 6t. Altogether, our solution set looks like this. This is called parametric form because we have the parameter t. We can also express the solution set in vector form. We have a column vector of constants and a column vector of multiples of t. X is equal to negative 4 plus t times negative 18. Y is equal to 3 over 2 plus t times 6. Z equals 0 plus 1t, or in other words, z equals t. The reason why this is called infinite solution is because we can pick any real value of t to get a new set of x, y, and z as the solution to this system of equations. Let's pick an easy example. T equals 0. X is negative 4 minus 18 times 0, negative 4. Y is 3 over 2 plus 6 times 0, 3 over 2. Z is 0. Put these values of x, y, and z into our system of equations, and we should see left-hand side equals right-hand side. Let's check. Negative 2 times 3 over 2 plus 12 times 0. Simplifying, we have negative 3. In fact, we expect negative 3. Right-hand side equals left-hand side. Putting our solution into the second equation, 2 times negative 4 plus 6 times 3 over 2, we have 1 equals 1. Left-hand side equals right-hand side again. Therefore, this is a possible solution set. X equals negative 4, y equals 3 over 2, and z equals 0. What happens if we pick t equals 1? X then becomes negative 4 plus 1 times negative 18, negative 22. Y equals 3 over 2 plus 1 times 6, 15 over 2. Z equals 1. Putting these values of x, y, and z into our system of equations, negative 2 times 15 over 2 plus 12 times 1. Simplifying, we have negative 3, which equals negative 3. 2 times negative 22 plus 6 times 15 over 2. We get 1. Left-hand side equals right-hand side again. Even if we pick an awkward value like t equals negative 2 over 5, we would in fact still have left-hand side equals right-hand side. So for any value of t, and there are infinite real values of t, we can get an infinite number of x, y, and z values that can satisfy this set of equations. Here we have a system of 3 unknowns, x1, x2, and x3. It looks like we also have 3 equations, but looking closely, the first equation and the third equation are multiples of each other. Multiplying the first equation by 3, we would get the third equation. So essentially, we only have 2 useful equations, but 3 unknowns. This is not enough information to solve the system. We have a case of infinite solutions. We can organize this system of equations into an augmented matrix. I put the coefficients for x1 in column 1, x2 in column 2, and x3 in column 3. Row 1 is going to be equation 1, row 2 equation 2, and row 3 equation 3. The first equation has 1x1 and 3x2, and the answer is 2. Equation 2 has 2x1, 6x2, 1x3, and the answer is 9. Equation 3 has 3x1 and 9x2, and the answer is 6. Since equation 3 is just 3 times equation 1, we can go row 3 minus 3 row 1 to cancel equation 3. We get a row of zeros. We've lost an equation, so we really only have 2 useful equations to solve this question. Let's try to cancel some more. Looking at the 2 and the 1, we can cancel the 2 by subtracting twice of that 1. Row 2 minus 2 row 1. 2 minus 2 times 1 is 0. 6 minus 2 times 3 is 0, 1 minus 2 times 0 is 1, and 9 minus 2 times 2 is 5. This augmented matrix is now in reduced row echelon form. Non-zero rows have a leading 1, and columns with a leading 1 have zeros everywhere else in those columns. We now interpret this augmented matrix. The second column, corresponding to x2, does not have a leading 1. We're going to assign parameter, let's say t, to x2. Equation 1 tells us 1x1 plus 3x2 equals 2. Solving for x1, we subtract 3x2 from both sides of the equation, replacing x2 with t. x1 is 2 minus 3t, and x3 we read off as equal to 5. The solution set looks like this in parametric form. In vector form, x1 has 2 minus 3t, so plus t and then negative 3 of that. x2 only has a t, so no constants and just 1t. x3 only has a constant, 5, and no t. In this system of equations, there are 4 unknowns: x1, x2, x3, and x4. We're also given 4 equations. By inspection, meaning by looking at these equations, equations 1 and 2 look like they are multiples of each other. Multiplying equation 2 by 3, we get equation 1. So we really only have 3 or maybe less equations to solve this question that has 4 unknowns. There are more unknowns than we have equations to find these unknowns. This is going to be a case of infinite solutions. Organize this system of equations into an augmented matrix. Column 1 is going to be x1, column 2, x2, column 3, x3, and column 4, x4. Equation 1 has negative 3, x1, negative 3, x2, 3x3, and negative 6, x4, and the answer is 6. Equation 2, negative 1, x1, negative 1, x2, 1x3, negative 2, x4, and the answer is 2. And so on. We put the information for the coefficients and the answers for equations 3 and 4. Since we already noticed that equation 1 and equation 2 are multiples of each other, let's start by getting rid of one of those equations. Row 1 minus 3 row 2. That will cancel equation 1. There's that negative 1 and the 1. We can add them together to cancel one of those. Row 4 plus row 2. 1 plus negative 1 is 0. And again, 1 plus negative 1 is 0. 1 plus 1 is 2. 8 plus negative 2, think of it as 8 minus 2, is 6. Negative 6 plus 2 is negative 4. Now looking at the negative 1 and the negative 2, we can cancel the negative 2 by subtracting 2 times negative 1. Row 3 minus 2 row 2. Negative 2 minus 2 times negative 1 is 0. And again, negative 2 minus 2 times negative 1 is 0. 1 minus 2 times 1, negative 1. Negative 7 minus 2 times negative 2 is negative 3. 6 minus 2 times 2 is 2. Looking at the 2 and the negative 1, we can cancel the 2 by adding 2 times negative 1. Row 4 plus 2 times row 3. 2 plus 2 times negative 1 is 0. 6 plus 2 times negative 3 is 0. And negative 4 plus 2 times 2 is 0. It wasn't so obvious when we were just looking at the equations without doing any manipulations, but after doing these row operations, we see that we've canceled another equation. So we now cancel 2 equations. We have a negative 1, which can be turned into a leading 1 in column 3. To get into reduced row echelon form, each column with a leading 1 has to have zeros everywhere else in that column. We have to cancel that 1. Row 2 plus row 3. Negative 1 plus 0 is negative 1, and similarly, negative 1 plus 0 is negative 1. Then we have the 1 plus negative 1 is 0. Negative 2 plus negative 3 is negative 5. And 2 plus 2 is 4. We need to get some leading 1s, not leading negative 1s. Let's multiply those 2 rows by a negative 1. This operation is easy enough that we can combine both operations into a single step. Negative 1 times row 2 and negative 1 times row 3. We just flip the signs from positive to negative and negative to positive in rows 2 and 3. And just for formality, reduced row echelon form wants us to put all the 0 rows at the very bottom of the matrix. We can interchange rows 1 and 2 and rows 2 and 3. The matrix is now in reduced row echelon form. We can interpret the matrix. Notice that we do not have a leading 1 for x2 or x4. We shall assign parameters to those variables. x2 will be s, and x4 will be another letter. Let's call it t. We're missing 2 leading 1s in this case, so for each missing leading 1, we're going to have a parameter, which is why we have 2 parameters in this case, s and t. Reading from the augmented matrix, x1 plus x2 plus 5x4 equals -4. Solving for x1, subtract x2 and subtract 5x4. Replace x2 with s and x4 with t. The augmented matrix also tells us x3 plus 3x4 equals -2. Solving for x3, subtract 3x4 from both sides of the equation. And replace x4 with t. x3 is -2 minus 3t. We can assemble the solution set in parametric form, and also in vector form. x1 is equal to -4 minus 1s minus 5t. x2 has no constant, 1s, and no t. x3 has -2, no s, and -3t. x4 has no constant, no s, and 1t.